The Rust standard library itself provides a huge number of traits. We're going to discuss some of what I think are the most important to be aware of, whether that's because you want to implement them yourself, you'll want to consume types that implement them, or because they have interesting knock-on effects you should be aware of. As ever, this series is accompanied by a free book. Check the description for a link straight to this chapter. My name is Daniel. Welcome to Iris. As it happens, there are a lot of really great traits in the Rust standard library, so many that I'm splitting this video into 3. This time we're going to discuss markers, derivables, and error handling traits, and next time we're going to discuss converters, referencing and dereferencing traits, and one other trait that didn't quite fit into any other category. Then we're going to have a little break to talk about collections before coming back to talk about the iterator traits. Before we dive into today's traits, I want to quickly cover something we brushed over in the last video. Traits can not only define the header for methods you need to write yourself, but they can also define methods with default behavior that you can optionally override. We call the methods you need to write required and the ones with default behavior provided. For example, in the last video, we defined the trait animal like this. In this case, getName doesn't have a body, so anyone implementing animal for their type must write it out themselves. This is a required method. If instead we were to write some default functionality, this becomes a provided method, which the implementers of the animal trait can choose whether they want to override or to use as is. It's up to you to decide when it makes sense to provide default behavior. In the case of animal getName, this default behavior isn't really providing anything meaningful. I think keeping it a required method with no default behavior is the right way to go. Markers are special traits that describe intrinsic properties of types. That is, they relate to what you might call the core essence of the type. That might not make much sense right now, but don't worry, it will. We're starting with a weird one here. Well, all markers are a little bit weird, but this one doubly so. You never need to implement size yourself. In fact, you can't, but you may choose to manually opt out of it, and it does have a use. Anything that is of known size at compile time is considered to be sized, and you don't need to specify this, it just is. For example, a U8 has a size of 8 bits, therefore it is sized. Cough. In fact, all primitives are sized, except for string slices, which you can't use outside of the reference form anyway, and references are also sized. Any compound type you create from only sized types is also automatically sized. So, if you don't need to implement size yourself, why am I talking about it? One place you will see sized a lot is that due to a quirk in Rust's design, generic types are always assumed to be sized. For this reason, you'll regularly see the trait bound $sized, which means that the concrete type, the one used to fill in the generic, may or may not be sized. While trait bounds usually have a restricting effect on what types can be used in the concrete implementation, this has a widening effect. For example, in the last video, I mentioned that I was printing a simplified version of the 2-string implementation for all types that already implement display. This was because I left out the $sized trait bound, so the 2-string implementation actually looks more like this. The plus means that the type T must abide both trait bounds, so T must implement display, but also does not need to be sized. You can, for complex but sensible reasons, opt out of sized by implementing not sized for your type. This is way beyond today's tutorial, but I thought I'd mention it because it's weird and fun. The copy marker trait means that the data the type contains can be copied, but copy actually has a very specific meaning in Rust. It means that all the data can be copied exactly as is. This only works, however, for types that exist purely on the stack. Let's take string as an example of something that can't be copied this way. String is a smart pointer that points to memory on the heap. The value of the string, the raw string slice, can of course be duplicated, but the string type itself is actually just a pointer to a location in memory. If we were to copy that location data, we'd have 2 pointers pointing to the same location. As soon as one of them is cleaned up, the data on the heap would also be cleaned up, and we'd be left with a string pointing at memory we no longer own. We'll talk more about how we can duplicate things like strings and other smart pointers later in the video. Types that can exist on the stack though can be copy. All primitives, again excluding string slices but including immutable references, are copy, and compound types built from those types can choose to implement copy. You can implement copy directly, though you must also implement a trait called clone, which we'll discuss later, but since both traits are derivable, it's very rare you'd ever do it manually. I'll show you that shortly. Now, one awesome thing that copy does is it changes how the language itself works. To reiterate, copy can only be applied to things on the stack, so the memory for a copy value doesn't need to be requested from the operating system like it would from the heap. Stack memory is pre-allocated and the actual copying part is very cheap. Because of this, Rust will use what are called copy semantics instead of the default move semantics. Unlike normal, when you reassign a variable or pass it into a function, if the data in the variable has the copy trait, the value is copied instead of moves. This means that you can still use the original variable after that's happened. So ordinarily we can't do something like this, you'll get a compile time error. However, for types that do implement copy, that code does work thanks to copy semantics. We haven't talked about concurrent programming yet, however, you might have heard that Rust is extremely safe and efficient when compared to many other languages. Much of that safety comes from the marker traits send and sync. We'll cover these in more detail in the future, but for now. Send is used when data can be safely sent between threads. When something is sent from one thread to another, it moves ownership, like when you pass a variable to another function. Sync is used when a reference to data can be safely sent from one thread to another. You have to be a little bit more careful here because this allows two threads to read and potentially write to the same location in memory. So T is send if it can be safely sent from one thread to another, and T is sync if a reference to T can be safely used across multiple threads synchronously. We'll talk a lot more about threaded programming later in the series, so don't worry if this doesn't make sense yet. Send and sync are like sized and can be automatically derived if all parts of your type are also send and or sync. Of course, you might still want to implement send and sync for types that contain non-send and sync types, and you can do this, but this requires us to delve into unsafe Rust, which isn't as scary as it sounds, but is beyond the scope of this video. For now, if you need to use non-send or sync types, there are built-in types to help with that, and we'll cover them when we get into concurrent programming properly. Apart from sized, send, and sync, most traits need to be manually opted into. However, for some traits, the behavior is so simplistic that the behavior of the trait can be derived. For most derivable Rust traits, there is a requirement that each child of your type also implements the trait you're attempting to implement yourself. To derive a trait, we use the derive attribute. Attributes can be defined either inside or outside of the type that they're for. However, like documentation, unless the attribute is being applied to a whole file, for example as a module, we exclusively use external attributes that come before the item they apply to. And, like documentation, we use an exclamation mark to differentiate the two. The derive attribute itself looks a lot like a function, and it takes a list of what look like traits but are actually what we call derive macros. Not every trait has a derive macro, meaning that not all traits are derivable. You can write your own derive macros too, though this is a very advanced form of metaprogramming we probably won't cover in this series. Many people do write their own though, so that they can provide custom derive macros for traits provided in their own libraries, and we will talk about that when we start talking about the wider Rust ecosystem. Debug is an extremely useful utility trait that creates a default way to write out types to places like standard out and standard error. Let's derive debug for a cat type like this. When printing a debug value, we use :question inside curly brackets for a positional marker. Or you can use it after the name of a variable like this. Ironically, perhaps you should try to avoid using debug for debugging. That's what a debugger is for. Head back to our getting started video if you need a reminder. Importantly, debug is required for assertion macros like assert_eq, mainly used in testing. If you assert eq to values and they're not equivalent, the test suite will want to print the values to the screen, and it wants to use debug to do it. We'll show this more when we talk about the equivalence traits in the next section. The debug trait is also useful for reporting during a running program, though be careful not to leak private information this way. This might be where you want to implement debug manually. We won't go into it deeply here, but debug works very similarly to display, taking a formatter as a parameter. EQ and partial EQ are Rust's equivalency traits. That's right, equivalence, not equality. What's the difference? What does equivalence mean, and why are there two traits? Allow me to answer those questions with another two questions. Is 0 equivalent to -0? Inside a floating point number, the binary representation is different, but mathematically, 0 is neither positive nor negative, so they are equivalent, right? Sticking with binary representations inside of floating points, it's possible to represent something that's not a number, or nan. Should two nans, even if they have the same binary representation, be considered as the same value when you can get there in different ways? Probably not. For the most part in Rust, we're only concerned with partial equivalence. That is what allows us to compare values with the == operator. Given what we've just discussed, consider this code. What do you think the output should be? Let's run it and see. This seems correct, right? You can derive partial EQ so long as all the parts of your type also implement partial EQ, or you can implement it yourself. Implementing it yourself can be really handy if you have a structure where some fields can be different, but the overall value is still considered to be the same thing. The official Rust guide uses books with ISBNs as examples, but just to be different, let's consider how you might also want this kind of behavior for aliased user information. Partial EQ has two methods, EQ, which is required, and NE, which is provided. Remember from earlier, we need to implement the required method, but can choose if we want to override the provided one. The default behavior for NE is not EQ, and I'm fine with that, but it's there if you need it. In this case, I'm going to say two users are the same so long as their ID is the same. Let's write a little test for this. If we derive debug and have implemented partial EQ, we can use the assert EQ macro to do that for us. Partial EQ has even more utility though. It's a generic trait where the generic parameter represents the type for the RHS, or right-hand side. This generic parameter defaults to being the same type, but we can write code that allows us to compare the equivalence of two different types too. Taking that user alias example again, what if we had a root user type and an alias user type? Now we can check if the user's equivalent to its alias. Bear in mind though that right-hand side means this equivalence only works one way around. You'll need to write the implementation for user alias 2 if you want it to go the other way around. So that's partial EQ, but what is EQ? EQ doesn't actually provide any additional behavior. It's an empty trait that can only be applied to types that are also partial EQ. Its purpose isn't to provide functionality, but to indicate to you, the software engineer, and anyone looking at your code, that types have exact equivalence. Remember those points I made about how floating points can have different binary representations but be considered equivalent, and they can be considered not to be equivalent when they have the same binary representation. This is not exact equivalence, which is why F32 and F64 do not implement EQ. There's no way for the compiler to guarantee the correct implementation of EQ, so it's something you need to be mindful of. Unlike partial EQ, EQ is not a generic that can be used with other types. Since we're talking about exact equivalence, this wouldn't make any sense. Earlier, we chose to make that user type partially equivalent if the ID matched. If instead we checked the entire object, it could be considered to be exactly equivalent. Of course, in this case, it'd be far easier and safer to use the derived version, which protects us from making mistakes in complex code or forgetting to check against changes that we make in our type later. As you can imagine, PartialOrd and ORD have a similar relationship to each other as partial EQ and EQ, and in fact, PartialOrd can only be applied to types with partial EQ, and ORD can only be applied to types with EQ, and PartialOrd. Both PartialOrd and ORD have one required method each, PartialComp and comp respectively, as well as some provided methods with default behavior. The required methods of each trait use the ordering enum, which looks roughly like this. PartialOrd is what gives us our usual greater than, less than, greater or equal to, and less than or equal to behavior through the use of the methods GT, LT, GE, and LE respectively. Unless these methods are implemented, their default behavior relies on PartialComp, which returns an option of ordering. Again, using floating point numbers, it's easy to see why we use an option on our comparisons. When comparing nan, is it greater than, less than, or equal to nan? We can't determine an answer here, so we use the none variant to represent that. One important thing to bear in mind when deriving PartialOrd is that although yes, you can do it if all parts of your type implement PartialOrd, there's a catch. When derived on structs, it will first check the ordering of the first field and only move on to the next field if the first fields are equal. To understand why that might not give us the behavior we expect, let's imagine a rectangle with width and height. By deriving the behavior for PartialOrd, Rust will first compare the width, and only if those are equal, then compare the height. This means that if the width is larger in one rectangle, then according to the derived behavior, it is the larger rectangle, even if the height of the other rectangle is significantly larger. For this reason, it's quite likely that you'd want to implement PartialOrd yourself, depending on how you think the type should be compared. Instead of using the derived behavior, let's create an area method for our rectangles and use that to compare them to each other. I think, in this case, this makes more sense. Finally, ORD isn't quite the same as EQ because it does have some methods. Comp, which is like partial comp and is also required, but returns ordering without the option. Max, which returns the greater of two values. Min, which returns the lesser, and clamp, which will return a value so long as it's between the other two values or the closest value there is. Like with PartialOrd, ORD can be derived but has the same ordering quirk. If we want to implement it ourselves, we only need to implement comp, and the other methods can use that for their default behavior. Importantly, when implementing both PartialOrd and ORD, the result of partial comp must match comp, though the compiler has no way of confirming this for you. The easiest way to handle this is you need to manually implement partial comp by simply calling comp and wrapping the result in an option. Let's update our rectangle. However, you may still find some weird behavior with clamp, even if you fixed comp, so it's another one you might want to override. Here you can see some weird behavior for clamp with our rectangles. Let's fix this by overriding the behavior. Clone is a bit like copy in that it allows you to duplicate values. However, where copy is implicitly very cheap, clone can get away with doing a bit more work. With copy, we can make a copy of any data that is purely on the stack. However, this restricts us to sized data. This means, for example, string, which is a smart pointer to the data on the heap, cannot implement copy. In order to duplicate string, we'd need to request new memory on the heap to place the data into, then copy the data to the new location, and create a new smart pointer on the stack to point to it. Requesting heap memory is what's considered expensive here, as you have to wait for the operating system to provide you a location you can use, so it's really handy to differentiate clone and copy. Luckily, you don't have to do all this memory allocation stuff yourself. For any type that is built from other types that already implement clone, you can derive clone. If you need to implement clone yourself, rare and only required in very specific and advanced circumstances, then you can. In order to derive copy, not only must your type be made only from types that also implement copy, but your type must also implement clone. This is easy to do with derive. Many types could be considered to have an obvious default state. Defaults for numbers are typically 0, while strings and collections default to being empty. If your type is built from only types that implement default, then you can derive default. The default behavior is essentially to instantiate your type with all their values set to their default. Obviously, this may not always be the desired result, so you can implement this trait directly. You might be wondering if you can derive default for enums, or if you have to implement it directly, and you actually can, using an additional attribute that you can apply to the value you want to be the default. Unfortunately, this only works when deriving default for unit enums, which means if your enum contains nested types, you will have to implement default manually. Hashing is the process of taking a usually arbitrary amount of information and distilling it into a fixed size of data. This is a one-way process, asterisk, but giving the same input will always give you the same output, and that is pretty useful. There are a lot of different ways to hash that are suitable for lots of different purposes. In Rust, there is a trait that describes a type that is hash, which means that it can be hashed, and another trait called hasher, which does the hashing. These traits aren't for general hashing though. In Rust, they have a very specific use. Can you guess what it is? The hash trait only works with the hasher trait and always results in a U64. This is rubbish for cryptography and security, but great for generating numbers for lookup tables. You generally don't need to worry too much about either trait, but hash is useful if you want your type to work as the key in a hash map or similar data structure. So long as your type is constructed only of other types that implement hash, then you can derive it, though if you need more control than that, then you can of course implement the trait methods yourself. This might be useful if you want to skip over some of the types that make up your compound type that can't be hashed, but if your type implements EQ, then if A is equivalent to B, then hash of A must be equivalent to hash of B. Wait, before we jump straight into the error trait, let's recap on display. This trait allows us to display information related to the type that implements it. Once you implement it, if you pass a value of your type into a macro like println or ePrintline or format, then display defines how that type will be rendered. Display has a single required method which takes a reference to self and a mutable reference to a formatter and returns a format result which has a type alias for result of unit type and format error. The easiest way to implement it is with the write macro, which returns the same type, and to use standard format so that you can reference things in the format module namespace rather than contaminating your own. The error trait should be applied to types that are specifically used to represent something that went wrong during the execution of code. Although results do not require the error trait to be implemented for types in their error variant, it is definitely worth doing as error types with the error trait provide a lot of utility. The trait itself has several provided methods but no required methods. You're unlikely to want to alter the provided behavior of the error trait, which means the only thing you need to do is to make sure your error type also implements debug and display. As we know, debug is usually derivable, so that just leaves display. See why I wanted to bring it up again? Let's create a custom error for a fridge to demonstrate how we might do this. We'll use an enum to represent the error states, which are either too warm with its current temperature, too cold with its current temperature, or an alert that the power has failed. We'll derive debug and we'll implement display, which just produces a nice human readable message. Finally, we can implement error, which will provide all the methods we need. While we've avoided talking about the wider ecosystem so far, it's worth mentioning that there are some extremely powerful error libraries that might change the way you work with errors. We will cover these in the ecosystem part of the series. Next time we're going to continue learning the most common traits, but I particularly want you to keep errors in mind as we're going to learn a very cool trick with them. If this has been useful to you, don't forget to like and subscribe, and I hope to see you. Hey, what are you doing here? Come on, we'll see about this. Okay, I wanted to sneak in a little bonus trait that I discovered while deep diving during a rewrite of this script. I got away without knowing about this trait for 7 years, so I don't think you need to know about it, but this trait is used in every single Rust program that you write, even the pre-built Hello World template that Cargo provides in a new binary project. This thing had been hiding from me in plain sight this whole time, and it blew my mind when I found it. If you've worked with other programming languages, you might be aware of exit codes or exit statuses. These are effectively a value that is returned from the program itself, usually returned from the main function when it ends to let the operating system know if a program succeeded or not. Different operating systems use different exit codes, so you need to be careful here, but usually exiting with a 0 means everything was okay, and exiting with anything else indicates that the program in some way failed. In Rust though, we don't return numbers from main. Usually, we don't return anything, right? Well, actually we do. We always do. Kind of. There is a trait called termination, and main must return something that implements it. Termination will provide an exit code via a required report method, and this is how we get our program's success or failure status. You may have noticed though that we almost never return something from main, but in Rust, when we don't specify a return type, the return type is the unit type. And of course, there's a built-in implementation of termination for the unit type, which will produce the success exit code, whatever that might be for your target operating system. This means that normally, so long as your code runs to completion and you exit your program by reaching the end of the main function, your program will be considered successful. You might have seen code examples, particularly hidden in documentation, where main returns a result, usually where the OK variant is a unit type. And this is because there's also a termination implementation for results, where the OK variant already implements termination, and the error variant implements debug, which, as we've just discussed, error types usually will. I've used both your usual no return style main function and main functions that return a result, and had thought that Rust was doing some magic here for exit codes, but never really thought to look it up. I didn't need to know this, arguably you don't either, but isn't it awesome when your curiosity leads you down a little path and you find something cool at the end like this? Anyway, that really is it this time. Thanks for listening to me ramble about this, completely useless bit of knowledge, and I will see you next time.